Look up at the night sky. Every star, every galaxy, every cosmic object you see is part of a universe that's expanding. But here's the mystery. This expansion isn't slowing down. It's speeding up. What's causing this strange acceleration? Scientists believe it's driven by something invisible, something powerful, something we barely understand. They call it dark energy. But what is dark energy? How does it work? And what does it mean for the fate of the universe? Today, we're diving into one of the greatest mysteries of modern science: dark energy. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. By observing distant galaxies, he noticed something astonishing. Galaxies are moving away from us, and the farther away they are, the faster they're moving. This was the first evidence that the universe is expanding, a concept that turned our understanding of the cosmos upside down. Scientists initially thought gravity, the force pulling everything together, would eventually slow this expansion. But then came a shocking revelation. In the 1990s, astronomers set out to answer a fundamental question: how fast is the universe slowing down? The assumption was that gravity, the force that pulls everything together, would act like a cosmic brake, gradually slowing the expansion of the universe. To find the answer, scientists observed distant supernovae, massive stellar explosions that serve as standard candles in the universe. These supernovae shine with a known brightness, allowing astronomers to measure their distances and track how fast galaxies were moving away from us billions of years ago. But instead of finding a deceleration, the results were shocking. The universe's expansion wasn't slowing down at all. It was speeding up. This discovery, first announced in 1998, completely overturned our understanding of the cosmos. The findings were so groundbreaking that they earned the scientists behind them, Saul Perlmutter, Brian Schmidt, and Adam Rees, the Nobel Prize in Physics in 2011. But the question remained: why? What force could be so powerful that it's counteracting the pull of gravity and driving galaxies apart faster and faster? To grasp the scale of this mystery, imagine the universe as a vast rubber sheet. Every galaxy is like a dot on this sheet. As the sheet stretches, the galaxies move farther apart. But here's the twist. The stretching isn't uniform. It's as if some invisible energy is pulling the edges of the sheet outward, accelerating the process. This invisible energy is what we now call dark energy. It acts like a repulsive force, opposing gravity, but its effects only become noticeable on the largest scales of the universe, where the vast emptiness of space dominates. Unlike gravity, which grows weaker with distance, dark energy seems to become more significant as space expands. It's as if the more space there is, the more dark energy exerts its mysterious influence, accelerating the universe's growth even further. One way to visualize this is by looking at the timeline of the universe. After the Big Bang, the universe expanded rapidly in a phase called inflation, then began to slow down as gravity started pulling things together. But around 5 billion years ago, something changed. Dark energy began to dominate, reversing the slowdown and initiating the era of accelerated expansion we see today. This timing is no coincidence. 5 billion years ago is roughly when the density of matter in the universe dropped below the density of dark energy, As the universe expanded and matter spread out, dark energy began to take over, and its effects have been growing ever since. Dark energy is thought to make up about 68% of the universe. It's everywhere, but we can't see it, touch it, or directly measure it. Scientists only know it exists because of its effects on the universe's expansion. So, what could it be? There are a few theories. One possibility is that dark energy is a property of space itself, an energy that's inherent to the fabric of the universe. Another idea ties it to something called the cosmological constant, a term introduced by Einstein to describe the energy density of empty space. But the truth is, we don't really know. Dark energy remains one of the biggest unsolved mysteries in physics. To understand dark energy, imagine the universe as a balloon. As you inflate the balloon, the surface stretches, moving points on it farther apart. Dark energy acts like the air inside the balloon, driving this expansion. But unlike a regular balloon, the universe's expansion isn't uniform. Dark energy's effects seem to dominate in the vast empty spaces between galaxies, pushing them apart. Meanwhile, on smaller scales, like within galaxies or solar systems, gravity is still the stronger force, keeping things bound together. The existence of dark energy isn't based on speculation. It's supported by several independent lines of evidence. One of the strongest pieces comes from observations of distant supernovae. These stellar explosions act as cosmic lighthouses, allowing astronomers to measure how the universe's expansion rate has changed over billions of years. The unexpected acceleration observed in these measurements is a direct sign of dark energy at work. Another key source of evidence lies in the cosmic microwave background, the faint afterglow of the Big Bang. By studying tiny temperature fluctuations in this ancient radiation, scientists have created a detailed map of the universe's early conditions. The patterns in this map reveal the precise balance of matter, dark matter, and an unseen energy, dark energy, driving the accelerated expansion. Galaxy surveys provide yet another line of evidence. These surveys map the distribution of galaxies across the universe, showing how they cluster under the influence of gravity. The large-scale structure of the cosmos, as revealed by these maps, aligns perfectly with the presence of a force counteracting gravity, dark energy. What does dark energy mean for the future of the universe? If the expansion continues to accelerate, we could be heading for a scenario called the Big Freeze. In this future, galaxies will drift so far apart that stars will eventually burn out, leaving a dark, cold universe. Another possibility is the Big Rip, where dark energy becomes so powerful that it tears apart galaxies, stars, planets, and even atoms themselves. But we're not sure. Understanding dark energy is key to predicting the ultimate fate of everything we know. Studying dark energy is incredibly challenging. It doesn't emit light or interact with matter in a way we can easily detect. Scientists rely on indirect evidence and advanced models to piece together the puzzle. Future missions, like the Euclid Telescope and the Nancy Grace Roman Space Telescope, aim to shed more light on this elusive force. But for now, dark energy remains a profound enigma. The universe is expanding, and so is our curiosity. What do you think? Could we one day unlock the secrets of dark energy? Or will it remain forever beyond our reach? Share your thoughts, and don't forget to subscribe for more journeys into the unknown.